Okay, we're happy to have Giovanni Villadoro tell us about open string Axiverse.
Thank you very much for the invitation, for the hospitality. So I'm going to talk about this paper with Rubin Petroshev, and this is going to be a talk about actions. I cannot start by anything else than the philosophy problem. Just another introduction to this. Oh, yes, thank you. The philosophy problem, but maybe I will give you a less orthodox introduction to what the strong CP problem is. In fact, for me, it's more like a puzzle. Specify what I mean. So the absence of the observation of any large neutron electric dipole moment tell us that one parameter of the standard model, one of the two parameters that can break CP, which is this combination of phases of the up and down Yukawa couplings, and theta naught, which is the coefficient of the topological term in QCD, is bound to be extremely small, less than 10 to the minus 10. And I remind you that the other phase that breaks CP in the Yukawa mass matrix, an off-diagonal phase that can break CP, instead has been measured to be order 1. So this is the smallness of this parameter is that as a strong CP problem. Of course, it's not, strictly speaking, a problem. It's not even a tuning problem, because in fact, it's just a parameter that happens to be very small in the standard model. There is no cancellation that you have to do, at least within the standard model or in many UV completions of the standard model itself. So it's more like why this parameter is so small. For example, analogously to why some of the Yukawa entries are very small. So now, the way I see the problem is when you try to embed the standard model in a full theory, in a full fundamental theory, then you would probably like to explain all the parameters of the standard model dynamically, like expectation value of fields, like it happens, for example, in string theory. So now, if you replace all the parameters of the standard model with fields, the expectation for the masses of these fields is going to be very high. So if you replace like a Yukawa or a modulus, or the gauge coupling with a dynamical field that will relax to the value we observe, their masses will be UV sensitive to whatever you put, heavy degrees of freedom you put. So you expect the dynamics that explain these parameters to lie at some very large scale, maybe the string scale, the Planck scale. This does not apply, strictly speaking, for instead the theta parameter. In fact, if you upgrade the theta term to a dynamical field, which is our axion, there is a chance that the axion mass gets most of its contribution from the standard model, from the gluon itself. If this happens, the potential that is generated for the axion will relax the axion to a minimum that exactly cancels this theta parameter, explaining why it is small. So we'll phrase the problem in the following sense, that the observation of no large electric dipole moment for a neutron is a strong hint that the associated degrees of freedom is actually light, that gets most of its mass from QCD. And this has interesting implications, because this will point to a new light degree of freedom beyond the standard model fields that can be tested. Experimentally, in fact, there have been a large effort to look for such light particle. And if this particle exists in the theory, at least part of the dark matter that we observe will be made out of this particle. If not, all the dark matter we observe. Feel free to interrupt anytime. So, okay, so maybe the most amusing part of the story is this connection also with dark matter. And the way dark matter is generated, axion dark matter is generated in the early universe, it's model independent, the fact that it's generated, but the amount that is generated is model dependent. It depends on the history, cosmological history of the universe. In particular, there are two main scenarios, the so-called pre-inflation and post-inflation scenario, which depends on whether the associated PQ scale, so I didn't mention. So there is a dimensionful scale in the way you couple the axiom to the standard model, which is this decay constant FA, which basically measures the amount for which the scale at which the shift symmetry of the axiom is basically the U1 symmetry associated to the axiom is restored. We can think this axiom as a pseudo-Goldstone boson associated to a spontaneously broken U1 symmetry, and FA is the decay constant of the axiom is associated to the scale at which the symmetry is spontaneously broken. So depending on the size of the scale compared to the Hubble scale in the early universe and the maximum temperature of the universe in the early time, basically you might be either in the pre-inflation or post-inflation scenario. So the pre-inflation scenario corresponds to the case in which at the end of inflation, the pitch-pin symmetry is already broken, so you already have an axiom. So in this case, our visible universe will experience only a particular values for the axiom, which is basically just selected randomly. And in this case, the amount of axion dark matter that you will end up with will depend on the initial misalignment, so on how far the axion field will find itself at the end of inflation. Unfortunately, in this case, the full amount of axion dark matter cannot be computed because of the ignorance of this parameter. And in this case, almost all the allowed parameter range for the masses of the axion and the decay constant could explain the totality of dark matter by just adjusting the initial misalignment value of the field accordingly. So unfortunately, this scenario is not very predictive. We don't have any reason to prefer any of these values. So in principle, the axion could be the totality of dark matter in almost all the allowed parameter space.
Why is it dark on that?
Okay, yes. So this is the allowed parameter space. So the dark regions are those that have been excluded so far. So in this region here, which correspond to small values of FA, means larger coupling to the standard model, these bounds are mostly coming from the cooling of star and supernova. Instead, this part here is correspond to masses of the axion that are close to the size of astrophysical black holes, and this part is basically excluded by superradiance. All the values in between are at the moment still allowed. If instead the scale of inflation and or the temperature of the universe in the early times were at any given point after inflation above this scale FA, at a certain point the PQ phase will be restored, and we will have a new phase transition in which the axiom will be generated afterwards. And at this point, all the information on the initial misalignment angle values of the axiom after inflation will be washed out. So in this case, the evolution is believed to proceed towards formation of topological defects. These are axion strings, vortices, and the evolution is understood to proceed through an attractor.
Sorry, what does it mean? What distinguishes post-inflation and inflationary? Why you said post-inflation? Like what
is post?
Who chooses?
Oh, this is just the relative size of FA versus Hubble during inflation, or Tmax, the maximum temperature of the universe after inflation. So if the maximum temperature of the universe after inflation is above FA, then you restore the PQ phase, right?
And you only break it later.
when the temperature drops.
And then it's what's
And then you have a
post-inflation.
topological
Okay,
deflation.
so it's all dependent by the reheating temperature. And
The reheating temperature or the scale of inflation. And this we don't know, right? So in principle, it could be in either of the two cases. But in the second case, since basically you become insensitive of the initial condition, the evolution goes into an attractor of these topological defects. Eventually, these topological defects decay into accidents. The amount of accident you produce is insensitive of the initial condition, only depends on the value of FA, which means the mass of the accident. So in the second scenario, in principle, the abundance of axion dark matter is calculable in terms of the mass of the axion itself. Unfortunately, the calculation is very hard because it requires to go through a nonlinear problem with large separation of scales. So despite all the efforts, there is still an order of magnitude uncertainty in what is this precise value, which we hope to improve in the future.
And this uncertainty is dominated by cosmology, not by QCD.
Is dominated by cosmology, by the evolution of the topological defect.
I don't think so. It's not by cosmology. It's dominated by your inability to compute.
Yeah, but
I'm part of cosmology. So.
No, seriously, it's because you guys cannot yet compute it well enough.
Yes.
Correct?
No, but I meant inability to compute what? The evolution of this network,
Yeah.
or details of QCD dynamics like phase transition. It's dominated really by network.
Okay. So in principle, however, there is a particular value. So in particular, it will be very important if this particular value will basically be determined with some reliability, because it might help experimental effort to focus at least for half of the story, half of the possibility, at least in one particular region of parameter space. So another aspect of the problem now is of the physics of axion is what is called the Peccei inequality. This has been already discussed on Monday. All the story holds if we assume that QCD is the main responsible for the potential of the axion. So how constraining is this assumption? So if we assume that there is extra breaking from other sector to the symmetry of the axion, to the potential of the axion, in order not to spoil the solution to the strong CP problem, this extra contribution must be subleading with respect to QCD, subleading by an amount which is at least 10 to minus 10, the bounce that comes from the EDM of the material. This means that any other correction to the axion potential should be at most 10 to the minus 10 times the contribution from QCD, which is here parameterized by the topological susceptibility, which numerically.
Sorry, can you explain for non-experts? This QCD is just cosine A over F, right?
Well, it's not a cosine, it's a little bit more complicated,
right.
but the prefactor of this cosine, it's some.
And what is this additional WPQ, VPQ?
This is, let's assume that beside the standard model contribution to the potential, there is some extra contribution to the potential of the axion that come from other sectors.
From your loops or whatever.
No, not from the standard model, from other physics.
From other fields.
Other fields and whatever. Yeah, or just write it to start with. Then I want to know how large it can be before I have to worry about it. Because of course, if this starts to dominate over the QCD, the minimum that this will produce will not be in general aligned with the QCD, and so the expectation value of the axion will not cancel the theta term in general. So this is more or less how small you want the extra contribution to this potential in order not to spoil the solution to the strong CP problem. It must be less than 0.2 MeV to the fourth power. Now, this will not be a problem in field theory, it just requires that the axiom has a good sheet symmetry that is only broken by the anomaly with QCD, with the contribution of QCD. But you might fear that this requirement start to be in tension with constraints that come from gravity. If the standard law in quantum gravity doesn't like any global symmetries at the fundamental level. So we have arguments to believe that in the full theory of quantum gravity, no global symmetry is exact. So if you want to be very conservative in this direction, then you will expect that at the Planck scale, there is no symmetry whatsoever. So all symmetry must be broken of order n Planck to the 4. And of course, this breaking is hugely larger than what you can allow, like by 88 orders of magnitude. So how a theory with no symmetries at all might lead to effective theories with good symmetries. So if you get inspired by how baryon number works in the standard model, you might require that, for example, this might happen if in the effective theory, the degree of freedom of the low energy theory are such that do not allow you to write any operators, any lower dimensional operators that breaks this symmetry. So the symmetry will appear at low energy as emergent as an accidental symmetry like baryon number in the standard model. So if you want to go in this direction, then you have to forbid operators up to dimension 10 to 40, depending on the scale FA, if it's low or large. Now you see that this is start becoming challenging from the model building point of view. There are models that achieve this 10, but of course now they require some extra assumptions on the spectrum, on the quantum numbers of the low energy theory, either using large rank chiral gauge groups, like it works a little bit in the standard model, or discrete symmetries, and so on. And at this level, now you may wonder whether these axiom models are more plausible than other solutions to the strong CP problem, like those based on spontaneous CP breaking or spontaneous parity breaking. Of course, these arguments are a little bit naive. So if you look a little bit more in detail, yes.
Is this dimension 10 to 40, is it related to imposing some discrete shift symmetry Z10 to Z4? If I were to impose a discrete symmetry, it would change.
Yeah, this is imposing no symmetry.
Okay.
So now if impose
because that power you have written there is assumed like implying to the force would change, right? If I impose on Z
large n symmetry, yes, you will start scaling. But if you don't have crazy n, this n to the 4 is just this is a dimension 4 operator. It's like n prime to the 4 times n cosine.
Right, but n would appear in the power of m Planck, no? Because if I write higher dimension operator, then I have to suppress it by the Planck scale.
No, this n prime to the 4 is just this the overall scale that appears in front of a PQ. This is what I call n prime to the 4. Basically, here I'm just saying that there is only n Planck as a scale.
Sure, I'm just saying if you say you have some complex field and you want to explicitly break the symmetry, but preserve Cn, then I should write something like phi to the n divided by m Planck to the n minus 4.
Yeah. This will be, yeah. This is one of the some of the solutions are based on this. Right?
Okay.
I thought that in any case in quantum gravity you expect even discrete symmetry
To be broken.
so that doesn't help. But on the other hand, why I'm trying to default? Because you're really only interested in the A-dependent part of the potential, right? So there is a big concern.
Yeah. Yeah, no, here be very super conservative. So I'm trying this n Planck to a 4 times cosine of the axiom of the n Planck. The worst case.
But I thought that was asking about discrete gauge symmetries or discrete global symmetries.
Is it could have had? Yeah, they could have. These are goes into this class. Okay. Okay, but so if you look now the problem a little bit more in detail, all the arguments that we have about the breaking of global symmetries in quantum gravity are coming from non-perturbative effect, black holes, wormholes. So we should really, well, it means that basically the reducible breaking of any global symmetries due to gravity should be non-perturbative. In fact, the only breaking that is in the standard model from QCD is non-perturbative, which is proportional to non-perturbative effects that scale like e to the -1 with this strong square. So once you embed this in a theory of gravity, this will be non-perturbative also in G string or G. So then if you take this approach, you will conclude that instead having a high quality Pechequin symmetry, just require that quantum gravity is you be completed a weak coupling, so that all the non-perturbative effects are exponentially suppressed, and then you should not worry about it. So you only have to worry about the PQ quality problem if you want to really construct a UV completed quantum gravity theory that embeds the string, because then you have to make sure that these are the largest contribution. In fact, there are examples in string theory in which these effects are the largest contributions to the breaking of global symmetries, in particular to the axial QCD axis.
But this is also a bit optimistic, right, to assume that the only source of breaking of PQ comes from gravity. Like in principle, there could be intermediate scales for any.
You can always break a symmetry, yeah, sure. You can always break a symmetry. This is, in fact, is the irreducible quantum gravity.
Yeah.
So you cannot go below that. Okay, so in fact, explicit examples of how that works, also discussed Marius in the brown bag, are those coming implemented by the string Axiverse, one of the authors here, and basically what you really need is very little. It's just extra dimensions and gauge fields, which are almost ubiquitous in string theory. So the idea is very simple. Imagine you have some extra dimension, you have some gauge fields that live in extra dimensions. Then there are degrees of freedom and low energies that are associated to Wilson loops of these gauge fields over cycles, over compactified circles that behaves as pseudoscalars in 4 dimensions, local pseudoscalars in 4 dimensions. And they can easily serve as axioms. Now, because this field in 4 dimensions actually arise from non-local objects in the extra dimensions, you will not be able to produce potential for the axiom by integrating out in the extra dimension heavy fields locally. So you can, by integrating out heavy fields in the extra dimension, you will not produce local operators that produce a potential for the axiom, because the axiom is intrinsically a non-local operator. To produce a potential for the axiom, you need to be able to produce a contribution for this non-local operator. And this is only possible if you have charged fields under the gauge group that winds that go around the Wilson light, like Alan Bob. So the first contribution to the axiom potential will arise by basically wrapping a propagator of a charged fields around this extra dimension. So if the mass of these charged fields are larger than the compactification scale, than the length, then this propagator will be Yukawa suppressed. They will be suppressed like exponential into minus n. So it will be, so basically you get an effective axiom field with a very good sheet symmetry by just requiring that the compactification scale, the size of the extra dimension, is larger than the Compton wavelet of the lightest charged field in the extra dimension. So this is the basic idea behind that. And in string theory, this gauge fields are ubiquitous. There are they typically come from Ramon, the Nemeshor deformed sectors, and they're associated to the closed strings sector of the theory. So they're always there. They're associated to the gravitational sector of the theory itself. So these fields that live on the bark will in general lead to, if the compactification is non-trivial, to many axion-like particles, low energies. And the requirement that the only charged states are heavy is automatic in string theory, because the objects that are charged under these gauge fields are objects like D branes or Nemeshor's 5 branes, which are with mass tension is always parametrically larger than the string scale if you are a weak couple, if G string is small. So this is, you can think it's like a monopole-like object whose mass goes like the string scale over some couple. This means that in any compactification which has a volume which is larger than the string scale, which you can trust in effective field theory, the associated breaking effects are always exponentially suppressed by the volume in string units of the compact cycle that is disrupted by the gauge fields and G string. And in several examples, if you replace this in terms of the effective four-dimensional coupling, they assume the typical form of like the small instantons effect. So you can even think of this contribution as the small instanton limit of the gauge theory, which are typically subleading with respect to the contribution that you get from QCD. Now, another properties of this type of axions is that the associated decay constant of this axion is always larger than the compactification volume. This means, this has important implications. First of all, well, it's from the point of view of pre-inflationary scenarios, this is good.
That's larger than the inverse compactification volume or the compactification?
1 over L is the compactification volume. So it's above the KK scale. It's above by some powers of the gauge coupling. So weak coupling is above. And so this is okay. This is good for pre-inflationary scenario, large FA axion models. But it's problematic if you want to realize the post-inflation scenario in this case. Because in order to restore the phase, you need to experience temperature that are above the compactification scale. In particular, the analogous of these vortices of these axion strings in this implementation are strings that are also charged under this gauge fields. But I said that the only objects that are charged under this gauge fields are D branes. So the actual strings, axion strings that will be produced by a PQ phase restoration in this case will be objects that are made of D branes. So the tensions of this object will be parametrically larger than M string, which means that you should, in order to be in the post-inflationary axion scenario, in this case, you should be able to, at a certain point, be able to produce D branes. Objects that are heavier than the string scale, which is challenging, to say the least.
And should I think of these effects as like the monopole strings associated with the gauge field and full vector theory?
Yes. The right intuition. So it's yes.
So when you say challenging, is challenging to compute, to understand, or challenging to actually?
I didn't specify because probably everything. It's challenging to reliably compute because this you need to produce the branes, but which are not perturbable in string theory, so you cannot use perturbable in string theory to compute this process. Besides, they're challenging also because they are in a cosmological setup, which is also challenging.
But we don't know what's gonna happen if we go in that.
Right. And also phenomenologically, because you want to produce these strings, at the same time, you probably don't want to produce other like monopoles or other stable objects that could be. This must happen after inflation, so you don't want to have stable element. Okay, so one question would be therefore whether one could realize a similar level of protections that is there from the string Axiverse for pre-inflation axion, also for this type of post-inflation axion, in which the decay constant of the axion could be actually parametrically low compared to the.
Sorry, what are you doing, Giovanni? Are you kind of trying to motivate some effective potential for the axions or what? Because obviously these things like don't exist, we don't care, right? So the question is, if I am interested only in observables, then for me, this is just a motivation for the
Yes.
ultimate.
For you, it's a motivation for the second part of the talk.
Okay. So I should just be patient. Okay.
Okay, so the idea is how to therefore to try to see if there is a framework in which we could have a similar protection for axion that, however, can experience a post-inflation scenario. And well, we found that actually this is very, very, very easy. All you need to know, all you need is to include to the construction of before localized charge fields. Localized charge fields are also generic in string compactification. They arise in many ways, from intersection of string of branes, from orbifold oriented for fixed points, and in fact they're unavoidable. For example, if you want to reproduce the standard model, which has chiral fields, you need to have localized charge fields in this dimension, otherwise you don't get the chiral spectrum. So what they do, so imagine that now you have some fields that are localized in the x dimension and charged under the gauge fields. Now you can consider gauge invariant combination of these charged fields. For example, in this case, I take phi plus and phi minus are two charge localized fields with charge plus and minus, and then I connect a Wilson line from one to the other, so that this operator now is gauge invariant. It's gauge invariant, but it possesses a charge under a global symmetry associated to a common rotations of phi plus and phi minus. So phi plus and phi minus, the charge plus and minus under a gauge group. I consider the other combination of phase rotations, which now remains as a global symmetry. So this operator is gauge invariant, but is charged under this global symmetry. And in fact, you can see that there is no operator which is charged under this global symmetry associated to these phase rotations, which is gauge invariant and local. All charged operators under these global symmetries that are gauge invariant are non-local. But this means that in order to produce breaking of these global symmetries, you need, like in the case before, charged fields in the bulk that can propagate from one side to the other and create a neutrino potential for this non-local operator.
Why they can be at the same point, the different fields?
Then it will not be localized. Yeah, if you have at the same point,
yeah,
charge plus and charge minus, they can. It's the limit when every goes to zero. Yes, then you could have a mass. But if the charge fields are separated, like when you generate chiral spectrum, then you have this.
But you're assuming the existence of this global symmetry now.
Huh?
No, this global symmetry is assumed exists. It's an
No,
assumption.
no, it's not an assumption. I'll give you this construction. These are, let's say these are complex scalar fields. I cannot write any term which is local, breaks this phase rotation, and is gauge invariant. Because locally, this rotation coincides with the gauge transformation. Therefore, if I want to generate any terms that breaks this global, must be non-local. So just take it also in 4-dimensional. I take 2 electrons. You have 2 phase rotations. One is the one you gauge. The other is a global symmetry. It's only broken by if you have something that goes from one side to the other.
What about other potential topological mass terms? Like I can imagine adding some like BF-like term for the.
Yeah, I'll
photonic
come
exit
to the, in the case of the string theory case explicit, I'll show what you get. So this now this discussion is only field theoretic, right? So if I don't put any charge fields in the bulk, but only the localized one, then I don't have any breaking of these global symmetries, and the breaking will scale like that.
Again, the operator phi plus phi minus at the same point is gauge invariant, but you're not allowing that. A master.
Yeah, the assumption is that here I only have a phi plus and here I only have a phi minus.
When you say localized, you mean that it's like sits
A
there.
delta function. Yes.
You like you put it there, you put it in the system.
Yes.
So is it good? So maybe that's what Gabriel was asking. Is it guaranteed that this PQ symmetry is a symmetry of that the PQ transformation is a symmetry of this theory? Because
Yes.
because on the gauge symmetry, phi plus phi minus have opposite opposite charges.
Yes. So the theory will have 2 independent phase rotation. One linear combination is gauged, which is the U1.
Yes.
The other linear combination, I claim it remains as a global symmetry, which can only be broken if you have charged fields in the bulk that generate this non-local operator, because all the operators that are charged under this PQ are non-local if you want them to be gauge in bulk.
Why can't they put phi plus and phi minus at the same point? Sorry, that's really.
No, if you put them at the same point,
Then
then
I cannot have master.
you cannot write a master. A local master in extra dimension, you cannot write it because it's non-local. So, couple of comments. So if you have n localized fields, then you will get n-1 global U1s. One linear combination is gauged, all the other combination of phase rotation will emerge as good global symmetry. On top of that, the PQ global symmetry now is linearly realized in 4 dimensions. So this operator here that basically is charged on the PQ symmetry, the associated PQ symmetry act on this operator linearly, and in particular, if phi plus and phi minus has 0 verbs, at least one of them, you basically you don't break the symmetry. So the breaking of the symmetry is associated to the verbs of phi plus and phi minuses. In particular, one linear combination of phases will be eaten by the gauge fields that become massive. The other combination remains as an axiom, and the other combination is basically dominated by the field that has the smallest verb, because the one with the largest verb will be eaten by the vector. So in this case, if the lightest of the smallest of the verbs of phi plus and phi minus is smaller than the compactification scale, the decay constant associated with this axiom can be parametrically smaller than the compactification scale. In particular, it can even be unbroken. So, and you can implement a full QCD axiom model. So this, I'll give you first a 5D toy example. Imagine you have one extra dimensions, which look like a segment. So if you want an orbifold. And imagine you localize phi plus here and phi minus there. And you have a U1 in the bulk. Okay? Now you see that the only operator that can break the discharge of the global symmetry is phi plus with some line phi minus is no longer. So if I want to implement the QCD axiom, I have to add also fermions. So I put also SU3 color in the bulk, and then I added a couple of fermions psi B, which are vector-like under SU3 color, but they are chiral with respect to the U1. And then I repeat the same pattern with complex conjugate charges on the other side. So anomaly is fully cancelled of the gauge. All the gauge anomalies are cancelled globally, not locally. This means that there must be some Chern-Simons in the back that flow the anomaly from one side to the other. The result of this is that there is an extra U1 global symmetry, which is this small number here, which is anomalous under QCD. And if the phi plus and phi minus gets a wave, basically it will produce an axion. So you see that on each side of this compactification, the matter content is exactly the one of the minimal so-called KSVZ model, in which you have basically a scalar field. The axion shear symmetry is some chiral symmetry. Phi gets a wave, is spontaneously broken, it's anomalous under QCD, you get the QCD axion. Now, in the limit in which one of the waves, let's say V minus, is much smaller than the others, you can decouple all these sectors and the bulk, and then you really recover the minimal model of QCD axion. In particular, to get, okay, so the axion shear symmetry is going to be protected up to exponentially small effects that I mentioned before. But since they go exponentially with the compactification scale, this compactification scale can be very small. It doesn't need to be much larger than the Planck scale. So all these extra dimensions could be above the gas scale, which means the theory looks exactly like a four-dimensional theory, KSVZ theory, all the way to the gas scale, which means that all the model building that has been done, for example, in this context, holds equally. So in the limit in which the wave of, instead, this field goes to infinity, you can decouple all the fields on this plane. And effectively, what they do is to give Dirichlet boundary condition to the bulk field. So now this is even a easier implementation of the model. You put all your axion model on one, four-dimensional axion model on one brane. You gauge the Pichy-Queen symmetry by putting the gauge fields in the bulk with Dirichlet boundary condition. And what you get is just the minimal model KSVZ, which now it can enjoy an exponential protection of the Pichy-Queen symmetry.
But don't you have good UV complete theories of axion which live just in 4 dimensions? You can, right? This KS.
Is this one that I put here? Right.
So then why go into extra dimensions if you can have good theories in 4?
This was the argument that if you believe that quantum gravity.
Because you want to avoid this quantum gravity.
Yeah.
Okay.
So this will allow you, if you want, to combine the models in 4D with the quantum gravity.
Okay.
In fact, this is now give the idea of how to uplift any global symmetry, any U1 global symmetry to be exponentially good. So imagine you take any 4D theory with a U1 global symmetry under which operator transform in this way, right, with the phase. So all you need to do is to gauge this U1 global symmetry, add an extra dimension, which the gauge fields is on the boundary, and put the Dirichlet boundary condition on the gauge field. So now, in the effective theory below the compactification scale, the theory is exactly the one you started with, the 4D, because the Dirichlet boundary condition means the gauge vector is heavy. But from the 5D point of view, the only way to break this global symmetry consistently is to generate an local operator. Now, this operator from the 5D point of view is not gauge invariant. To make it gauge invariant, you have to dress it with the Wilson line that goes from here to there. Now it's non-local. So all the breaking of this symmetry will be exponentially suppressed if the charge fields under this A mu are heavier than the compactification scale. So in this way, you can uplift any global symmetry from the 4D point of view to an exponentially good theory, good symmetry from the point of view of the UV control.
So you need to respond in dot anomaly dimension so that we can gauge.
No, if this U1 global symmetry was anomalous, you have to add also Chern-Simons stamps on the back.
And still can do the same. Okay.
But for the axion, you have
Right,
to add
yeah.
the Chern-Simons.
Mhm.
So the breaking will be exponentially suppressed. And notice that from the 4D point of view, these global symmetries do not appear as an accidental symmetry. You can write lower dimensional operator break the symmetry from the 4-dimensional point of view, but they are simply have an exponentially small coefficient. So this is, if you want, is a way to reconcile the ancient method of applying global symmetry by hand in the effective field theory with the more modern law that all global symmetry are broken in quantum gravity.
Sorry, if the symmetry is anomalous, wouldn't the Chern-Simons simply shift the anomaly to the other side?
But because of dirichlet boundary condition, then they can't happen. Which dirichlet boundary condition means that there is some heavy fields that compensate this anomaly, but it's heavy. Okay, so let's now, I wanted to comment on how, so all what I said assumes that all the charged fields are heavy enough that all the effects are exponentially suppressed. But I want to show that this is automatic in string theory also in this case. So maybe the simplest realization of this localized charge field, you can think in the following way. Imagine you have 2D branes intersect twice. On the intersection, there are charge fields, which are the strings that stretch from one side to the other, which are localized to live there, and which are charged under the U1 that live on each brane. So they're bifundamental of the 2D branes. And they have opposite charge. There is no other charge fields in between, because the only charge fields would be strings that stretch from one side to the other. But as you try them to move them through, they will be stretched, which means their effective mass will grow, like the linear size. So if these branes are separated by more than the string scale, all the modes, charged modes from one side to the other are heavy. So you can construct the analogous gauge invariant operator that involves phi plus and phi minus by just dressing Wilson lines that lives on the boundary. In string theory, you also have to put a B field because there is some mixed gauge transformation between A and B fields that live on the surface between these 2D branes. And this potential can be created in string theory. And indeed, it's produced by exactly these strings traveling from one side to the other. So the effect will be proportional to e to the minus the worldsheet action of the brane stretching between these 2D branes. So as long as the separation between phi plus and phi minus, the intersections, and the 2D branes is large compared in units of string scale, you'll get an exponential suppression of this contribution.
And you can keep this brane configuration stable, like I would worry about dynamics of the extra dimension.
Yeah, so from this picture, it doesn't look stable.
Yeah.
They like to
come
be
together.
separated. But there are ways to realize it in a stable way. There is an extra contribution that you could have, another gauge invariant operator now constructed with the Ramon fields. And this will be generated by Euclidean de-brane instantons that are, for example, this dashed line here. And again, the associated effect is exponentially suppressed. And indeed, this is the direct analog of what was happening already in this closed string case. And there is no other contribution in theory. Of course, this is was well known in string theory. So this type of construction has been constructed before in the past. So here I just want to highlight how generic these constructions are. So if you want to realize the full QCD axiom, just add the stack of three branes that reproduce SU3 color. And now you see that this construction is very similar to the 5D toy model. Here you have phi and the two fermions, phi and the two fermions. There will be some Yukawa from the worldsheet instanton here and there. So this will give you a case VZ and a case VZ star sector, which will reproduce the 5D toy model that I have. Okay, so you might imagine that in a realistic compactification that is able to produce the standard model and all the physics that you need up to the string scale, there will probably be many of these intersection and fields. And so you might expect that there is a chance that at least in some of them, you will have light axions with low decay constant. But in realistic scenarios, they probably need some supersymmetry to stabilize these scalars that lives on the boundary to be light. The decay constants therefore associated to the bevels, these scalars, which you might expect to be linked to Susy breaking, so the Susy breaking scale. So as long as the Susy breaking scale is small compared to the compactification scale, you might expect the associated decay constant also to be.
Why is it called decay constant?
Oh, it's like for the pions because it controls
Decay into two
photons.
Okay.
Okay, so now you can use this motivation to look for what this will imply in the searches of axion-like particles. So this is the common plot of masses versus coupling for axion-like particles. This green region here is what you typically have if the axion couple to photons. You'll have astrophysical bounds from astrophysics that lies at large coupling here. The difference in this other Axiverse is that there is now a new opportunities to look for this axion fully gravitationally. So there are ways in which this axion will manifest themselves just by the fact that they are produced in a post-inflation scenario. And these are this blue and orange region. So I can briefly comment on those.
But just the fact that the decay constant is below the reheating temperature doesn't guarantee that the symmetry gets restored, right?
No, they must couple to the infraton. They must be reheated. So let's see. So these are all the blue regions are bounds that only uses gravitational coupling of the axion. So if the axions are light enough, then it means that in the post-inflation scenario, the strings that are associated to that are produced in these post-inflation scenarios survives after a combination.
I'm sorry, how can it be this light? Then it is not dark matter.
Not dark matter.
Oh, it's not dark matter.
This is a full parameter space. So there are dark matter on this region. So let me start.
Okay.
So there's dark matter in this region, in this line here. This is excluded because it give you too much dark matter. All the region above, it give you less than the dark matter we observe. Okay. These are the bounds coming from superradiance.
So you are not solving dark matter problem, you are looking for axions.
Yes, well, both. Here I solved the dark matter problem. Here I partially solved the dark matter problem.
So the superradiance goes away at low F from self-interactions?
Huh?
The superradiance goes away at
Because
low
of
F.
self-interaction. Right, so this is the region will reproduce exactly that matter. Then you have a bounce here from isocurvatures because this axion you produce also have a small scale isocurvature from the fact that the axion are produced not from misalignment, but from the decay of these topological defects. And you can look for this isocurvature. This is the contribution from the wide spectrum regions of the axions gas. Here you have bounds from CMB, delta and effective. The strings also produce gravity waves. So if the tension is large enough, they actually could be probed by LIS and SKA. So if the decay constant is large enough,
Here you mean cosmic strings.
Cosmic,
Okay.
the real one.
The real one. Okay.
And also you could get a signal in delta and effective because the strings will also emit relativistic axions that in principle could be probed by next generation CMB expert. For the QCD axion, the relevant parameter region is here. So this segment here is where you get the right matter abundance for the QCD. It's a segment because of the uncertainties in the estimates. The dashed you get less than the dark matter abundance. And this is the line, the prediction from QCD, the relation of FA with the main. This orange region here instead is the region where you can fit the right matter abundance if this post-inflation scenario axions have long-lived domain walls. So unlike for the QCD case, you could have axions which also produce the strings that at the end of their evolution produce stable or semi-stable domain walls that therefore survives longer. And in such a case, you'll have you could in principle populate also this region of parameter space with the right parameter. This now depends how long-lived these domain walls are, which is a free parameter. You cannot extend more than this because then you start to get too large isocurvature that can be observed, for example, in landscape structure. Okay, but the interesting feature of this basically open string Axiverse is the fact that there are a way to explore this axiom also in the region that would be hopeless from the point of view of direct searches.
Why is your QCD dark matter is not on the line of general?
Right, because okay, for this axiom, I'm assuming that the mass does not depend on the temperature.
Okay.
Instead for the QCD axiom.
Do the cosmic strings have any meaning in the extra-dimensional theory? Like, should I think of them as being made of these branes, or is it, or what's the scale hierarchy here?
Right. So here for this plot, I'm assuming that the decay constant of the axion is parametrically smaller than compactification scale, so they're fully four-dimensional. Otherwise, things become more complicated.
Yes.
They're really
Giovanni,
complicated.
So to make this plot, you could have known nothing about the first 50 minutes of the talk, right? Okay.
In fact, yeah, these bounds were already there in the literature by just assuming post-inflation.
So you're just saying this is now a post-inflationary
Axiverse, yes,
scenario is more likely because now you don't produce deep brains.
Yeah, all my talk was mostly motivation for this plot. And the remaining 2 minutes, wanted to say something more about. So I mentioned that there are some isocurvature effects from the decay of this string and domain walls that have observational consequences, and they are particularly interesting for the actual QCD axiom. So let me see if I manage to say everything. Maybe just show you the cartoon and the results. So let me just recap how things work for in this post-inflation scenario that I didn't have time to comment much for. So at some point in the early universe, you restore the PQ phase. At this point, you produce strings, these vortices that evolve. And during this evolution, at early time, you can neglect the mass of the axion. So basically, the axion behaves like relativistically. The evolution proceeds until the axion mass, the axion potential become relevant. And this happens when Hubble reaches the mass of the axion. At this point, you form domain walls between strings that will attract the strings and collapse the network. There is some nonlinear regime. And after that, you produce non-relativistic axions that just shift like non-relativistic matter with some non-trivial spectrum distribution. Now, what we found is that the story is even more complicated than this, because there is a second nonlinear regime while the actions are non-relativistic, because the Portic coupling is important because it's still growing with the temperature during the evolution. And what it does is it doesn't affect the axial abundance because the axion is non-relativistic, so the number densities of axion is common. The common number density is conserved, so the axion abundance is the same. But the spectrum changes, so there is a redistribution of momenta due to the self-interactions of the axion in that regime. And it turns out that thanks to that, these non-homogeneities, these isocurvatures produced by the decay of the topological defects are such that at matter radiation equality, they clamp into solitons, into objects that look like Bose stars. Don't have much time to explain in details.
Eventually they evaporate?
No.
No? So
So
Yeah, he didn't tell the most interesting part of it, that today 10% of dark matter, according to him, is an axion stars.
right, so
That was the point.
So I'll give you the results. So this results come from simulations. So what we simulate is Schrödinger-Poisson equation on a lattice during matter radiation equality, inputting the spectrum that you will get from the decay of topological defects. And what we find, because there is a coincidence between where the peak of the distribution of axion is from the strings and the gene scales, the quantum gene scales at that time, the object that collapse, they collapse into objects that have a de Broglie wavelength of order the size of the object itself. So they look like a Bose star. So this is the result of simulations that shows the fraction of dark matter that ends up into these Bose stars as a function of the redshift. This should be A already. So this one is matter radiation equality and later. So you see that almost independently of the initial spectrum according to the most plausible values of FA for the post-inflation QCD axion case, more than 10% of dark matter is in these axion stars. So this is a snapshot of the simulations. For example, for this particular point, you see that they are clearly visible, these points here, these axion stars. This is a zoom in. You see that these are clumps of dark matter, gravitationally bound, and the size is similar to this interference pattern that tells you that the typical de Broglie wavelength of the dark matter axion is similar to the size of this object.
Okay, delta is where
The
delta.
peak of delta over rho. So depending on different from 0.3 to 4, because the more UV is, the more it takes to. So this is one of these Bose stars. So this shows instead the profile of the density of all these points here, compared to the density to the profile of a Bose star. This is from basically numerical calculation of the Bose star equation. So you see that all these profiles nicely fit the Bose stars up to 90% of the density. At larger distances, they deviate, and this is mostly because the stars are not in vacuum, but they are inside some bigger cluster. They are hosted by larger clusters. So this dashed line instead is the amount of dark matter into bigger cluster that host this star.
what is the scaling? What's the power law index outside of the solid zone regime?
Do I remember? I remember it was one of the largest explorer, but there are larger uncertainty because we don't have a lot of statistics there. So also, because it's part of the halo of the. Yeah. It wasn't incompatible with NFW, but the errors are very large. The properties of these stars, on the other hand, depends a little bit on the value of FA that give you the right dark matter abundance. The most plausible one, given the most recent simulations, are I would say the last three. And you see that these stars will have a mass between 10 to the minus 18 and 10 to the minus 19 solar masses.
Like an asteroid.
Like an asteroid, and a size which is 10 to the 6 kilometer, which means more or less Earth-Moon distance, and a density which is a little bit smaller than the density matter addition equality, which is let's say 4 orders of magnitude higher than the average dark matter density in the Milky Way. So it would be an over density of 3-4 orders of magnitude with respect to the average dark matter. But because the masses of this object is very small, and the 10% of the dark matter are made of these both stars, if they survive until today, then you will expect that the interseparation of this average interseparation of these objects will be like astronomical units. There will be many inside the solar system, and on average, we could have an encounter of the Earth with one of these both stars every 5 years, and the encounter will last like 8 hours. So this will mean that if you had a axion experiment which is already tuned to the right dark matter mass, you will see a boost of 4 orders of magnitude in the signal for 8 hours every day. Unfortunately, we've not been able so far to come out with alternative ways to probe this scenario, but I hope some smart way will manage. And I think the most appealing part of this story is the fact that this is what is expected to happen almost independently in this post-inflation scenario for the QCD axion.
So this whole discussion was for QCD axion.
This is just for the QCD axion. For the other apps, actually, it doesn't work. They don't form both stars, they form more milligrams. It's because of temperature dependence on the QCD axion.
But the amazing part is very hard to rule this out. I mean, because you would think asteroid mass, clumps of dark matter, really? What kind of nonsense? But apparently it doesn't contradict anything.
And with this, I conclude. I hope you managed to convince you that this post-inflation scenario is well motivated and deserve further efforts and studies. And at least for the QCD axion, it has potentially very interesting phenomenological conflict. Thank you.
Good question. These axion stars, do they interact with each other?
Good. These are solitons. So for solitons, what happens is that if they collide with the relative velocity, which is less than the escape velocity, what typically happens is that they merge and part of the mass is expelled. But if the relative velocity is larger than the escape velocity of each star, they just pass through unaffected. So at the beginning, when they form, you expect them to merge because the initial velocity is 0. But as you start forming bigger and bigger clusters of stars, they virialize. So the virial velocity is larger than the velocity, the escape velocity of each star, and then nothing will happen anymore. In fact, we see some mergers in the simulation itself, but we are not able to simulate long enough to see bigger cluster forming of stars.
Do they survive really? Tidal disruption?
So we did estimates, and it seems so. These are the most compact object made of dark matter, so they resist with respect to any tidal disruption of dark matter halos. Instead, when they pass through the disk of the galaxy, they get disrupted. Sorry, they have a chance to be disrupted, which is non-trivial. But it seems that most of them will survive. So if a star passes through the solar system, will be disrupted. But it takes long to disrupt, it takes much longer than the time it takes to pass through. So it will pass through unaffected, and then after it leaves, much longer after, it will break apart.
They form a disk
Huh?
and they form a disk. They remain in a spherical halo or can they form a disk over
You mean in the
in the
galaxy?
galaxy? Yeah.
They
I
are just
think- I
like
think
dark
they
matter.
will just
right?
do some they will just destroy. I don't think they will remain in the disk. They will just pass through the disk.
Yeah.
They will destroy and.
But there is no difference with the usual dark matter, right? It's just that 10% of it is in clumps. That's it, in stars. Otherwise, it's exactly like the normal collisionless dark matter.
So if it's not collisionless, they can merge, for example.
No, but they
Rare.
don't merge anymore. You have to tune the velocity. So the escape velocity of these things are millimeter per second. So you need to take two stars which only move millimeter per second to merge. They move more than millimeter per second, they pass through each other.
And once they're disrupted, they stay disrupted or they.
From discovered by baryons,
Yeah.
I guess. I don't know.
Then it's a contribution to the smooth background.
Yes.
Yeah.
It starts phase mixing.
And most of them they don't pass close enough to stars to be disruptors.
To Sergey's question, in the ALP scenarios, if you have post-inflationary phase transition, but not for the QCD axion, you do expect some order one density perturbations that are very small.
Yes.
So
So
yeah,
for,
what
but they
happens?
don't look like both stars, they look like these mini clusters.
But
I'm
Yeah,
not
it's
sure.
but it's more or less the same, right? They're still very dense clumps.
They're heavy. Well, okay, now it depends on the parameters. Yes, because of course it depends where you are with the mass.
But you're saying those dense clumps
They're
are more,
typically
in a more
much more
excited
dense.
state.
They're much more dense. Well, at least in this part of the plot, but the mass is smaller, the object, the scale will be larger,
Because of it's a lower mass.
and then it will be heavier. Which
Right.
means that the number density of this object will be less.
But it's still the same, but let's say they still collapse at matter radiation equality roughly,
Yes.
and they still have a soliton like
They might develop a soliton
in the
core.
center.
Yes.
But you're saying instead of an isolated soliton with a little bit of,
No, but there will be many less solitons in this case. because
Okay,
there
so
will
the
be one
solitons,
for
yeah.
each big object.
okay. With a subdominant mass in the soliton. Okay.
And also this bigger cluster, I think they're more susceptible to tidal disruption. And the small compact. Don't know what to expect.
What is the value, the maximum value of theta, the center? It's still tiny and small.
10 to the minus 16, maybe? Because it's more or less the value theta matter radiation equal.
Still
Nice.
Maybe more.
Thank you.